Okay, let's continue the journey. The journey. The slog. Hopefully it's not a slog. Hopefully we're learning. So we're going to finish up the chapter on carboxylic acids, esters, amines, and amides. So that's where we're at. So today is a day on amides, and then we will be done with this chapter. We're going to move on into proteins and amino acids on Friday. So yeah, this is it's kind of a fun day, fun lecture. So what's the take-home message on amines? Water soluble is good. What's the number one thing you should think of when you think of amines? There's two things. What's number one? There's two of them. What are the two things you should think of when you think of amines? Okay, it's a nitrogen, but that's just the atom, that's the element that it holds. Yeah.
They're bases.
They're bases. Number one is that they're bases. Okay? And because they're bases, number two is that they form water-soluble salts. Okay, if you took nothing from Monday, that's the most important thing. Bases react with acids to form water-soluble salts. So we had this whole thing on the term freebasing, right? We don't take morphine in the hospital with a cigarette or a lighter and a spoon. We take it in a water-soluble form. Could you imagine out on the field, right? Just like, here, take your morphine. So we don't do that. We take it in either a tablet or a water-soluble salt. Okay? Good. Okay. So that's really the take-home with amines. And like I said, amines and carboxylic acids are by far the most prominent functional groups in all of medicine because they make salts. Carboxylic acids make salts. Amine bases make salts. Salts are water-soluble. We're aqueous beings. Therefore, we need to have a molecule that our body recognizes. Okay? So that's really important with amines. Amides are probably, and the kind of the cool thing with amides are oh, Jack, you come down here. Missed you on Monday. Yes, sir. You weren't your normal spot. One chair away from Christian. I know right where you sit. Right? So, with the amide functional group, the amide functional group has a special bond, and it's this bond right here. Okay? And just like with esters, when I took the blue pen with esters, this makes this the special bond. Now, here's the cool thing about amides. You already know the chemistry. If you know the chemistry of esters, you know the chemistry of amides. The only difference is instead of getting an alcohol out, you get an amine out. So we've already seen that, and by the way, this is our final organic functional group. So we've literally climbed Mount Shasta, or Mount Lassen, or Mount Rainier. And we've come to me, one of the most important functional groups, the amine and the carboxylic acid when we're dealing with medicines and drugs within the body, again, because they make salts. But the amide, we'll see next chapter, is the bond of life. This is the bond that is made between all amino acids in enzymes and proteins. Okay? This is a really important bond. And when we get into amino acids, when we get into enzymes and proteins, you're going to see that the amide bond comes from the carboxylic acid and the amine. Okay, and we'll see that today when we start to make these. So the very first thing that we want to do is understand how to describe them. They're kind of weird in the way that we talk about them. So if I have an amide that looks like this, if I have an amide that actually looks like this, this is going to be, and again, if you remember back to ester nomenclature, that's our special bond, carbonyl nitrogen. Ester was carbonyl oxygen. Special bond, it's the bond that hydrolyzes, and that's the bond that's going to saponify. Okay? Well, and again, that's the chemistry of it. In nomenclature, just like if this would have been, it's similar to if I would have had this molecule. Notice they're somewhat similar. This one, because you had it, would be ethyl butanoate, right? Ethyl, special bond, 1, 2, 3, 4, butanoate, okay? With the amide, what happens with these is because the nitrogen can actually have 2 branches coming off of it, whereas oxygen always has 2 bonds. So I don't need to say oxygen ethyl. I know the ethyl's coming off the oxygen. But here, because nitrogen can have 2 functional groups coming off of it, I have to say this is an N, and it's capital italicized N, ethyl, okay, butanate, or butamide. A lot of chemists call them amides. I do hear amide every once in a while. I don't really care. Amines are amines, they're not amines, but I do hear amide or amide, and they're both accepted. It's just one of those things. And I think the amide, I don't think the E makes the I hard as a general rule. On this, just like amine and amide, not amide, but I don't care on this one, because I do hear amide a lot. So the N describes where the ethyl's coming off. Why is that? Well, because if I have multiple functional groups coming off of this thing, whoops. If I have multiple functional groups coming off of this amide, okay, something like this, watch what happens. This is my special bond. Okay, so this is carbon 1, 2, 3, 4, 5, 6. So what do I have? Well, I have an N-ethyl, alphabetical, dash, N, comma, 4, dimethyl, hex, N, amide. Okay. So it looks a little bit weird, but when we're dealing with nitrogen compounds, we just treat the nitrogen as an N instead of a number. And that's just kind of the weird amide nomenclature. So again, back to the very first rules in chapter 11. We circle the longest chain that includes the parent functional group, which is right there. Okay. We circle all branches. Here's a branch, here's a branch, and here's a branch. Okay. So one of the branches, alphabetically, the E, the first one, is coming off of the N. So I say it's N. Capital N dash. We treat the N as a number. So we put a dash between it. It's just one of those rules that they came up with to describe amides. Because I have 2 methyls, again, I don't alphabetize on the di, I alphabetize on the M. So this is going to be M and E. So with that, where are my methyls? Well, one of my methyls is on the N, and one of my methyls is on carbon 4. So it's N, comma 4, dimethyl, hexanamide. Okay? Questions on that? No? Good?
Why is there not, why is it a comma between the N and the 4?
Yeah, because the N is considered a number. Capital N is considered a number.
Italicized.
Yeah, yeah.
So both of those ends are italicized?
Yeah, they're both italicized. And it's hard to do it
Right.
when I'm writing it, but you'll see that. That's just kind of the convention. And I don't really care that it's italicized, but they are. Okay, so let's have you name one. All right, that will be fun. Go for it. Forgot my cup. Get it? Okay, special bond is the bond between the carbonyl and the nitrogen. So I'm gonna take my blue pen. I'm gonna throw that pen down. So that's my special bond. So that's the one that orients me on the carbonyl and the nitrogen. So because the special bond, carbonyl is on the left, this is my parent name. So this part of the molecule here is my parent. So I'm going to call that, because it's carbons 1, 2, 3, and 4, I'm going to call that butanamide. Butanamide. coming off the butenamide? Well, I got a lot. I got a methyl, I've got a propyl, and I've got a butyl. So what comes first? Pretty good. So then butyl, dash, good.
And purple.
Propyl or methyl?
3 methyl.
Yeah, 3-methyl,
I don't
dash,
like the alphabet.
and propyl. Okay. Questions on that? Yeah.
Is there a reason you called it butamide over here and butamide over there, or?
Did I mess it up? Butane. No, so, did I mess it up? This is wrong. So, thank you for finding that, because that's actually important. It's butane, right? And we lose the E, and it becomes amide. So that is incorrect. So this should be butanamide. Thank you for fixing that. It's those little subtle things like that. God darn it, that's my 4th mistake over my quota of 3. Okay. Good? What's that? Let's make it less complicated, right? That's actually awesome. Okay, I won't. That's it. And here's the thing. You're finished with nomenclature. So hopefully now you can name all the functional groups of organic chemistry. And I will review those. I'll review those either on Friday or when we get back from spring break. We'll go through all of the organic functional groups. Okay, so let's talk a little bit about the chemistry of the amide functional group. The chemistry of the amide functional group is very similar to the chemistry of the ester group. So that's nice, you've already seen this chemistry. So the only difference is instead of an alcohol, we have an amine. So if I take let's do 2 main reactions. So if I take an amide, okay? If I take a generic amide, again, where R's can equal hydrogen or carbon, and I subject them to acid hydrolysis. So this is going to be acid hydrolysis. Okay, acid hydrolysis. Again, my special bond is right here. That doesn't change. Just like with esters, amides are similarly hydrolyzed. I'm going to put water across this thing. Okay? That's what hydrolysis is, adding water. So I'm going to put an OH on that carbon. I'm going to put an H on that nitrogen. That's all I'm doing. When I put that line through there, I'm really just removing that bond. And I'm removing that bond. And you can see that NH, carbon OH. That's all you're doing. Okay? So I can do it more easily on the whiteboard than you can in your notes. But that's all we're really doing. Okay? So the product from this is going to be carboxylic acid, just like with the ester. And if you want, I'll do it in blue, just to show you where the water came from that. Okay? And to be technical, even the electrons should be blue because they do come from the water. So there's what it looks like. Plus H, N, R, okay? So that's the acid hydrolysis of an amide. So my functional groups here are an amide, hydrolyzes under acid conditions to a carboxylic acid. And an amine. Okay? Under saponification conditions, where I just hit it with sodium hydroxide, and we'll also do add a little bit of heat to this. I'm going to go to the carboxylate salt. And the amine. Okay. So these reactions literally are identical to esters. Amides are not, they're not as reactive as esters, so it does take a little bit more oomph to get these things to break up. But if anybody had protein for breakfast, whether it's almonds, peanuts, milk, eggs, porcine, bovine, equine, fowl, whatever you had, you probably didn't have equine, that would be kind of gross. But if you had any protein source for breakfast, the HCl in your stomach right now is about 2 molar, and it's actually doing this reaction right here. It's breaking up the amino acids from the protein source that you ingested, basically to the carboxylic acid and the amine. And the reason for that is because the amino acids that made up the porcine, if you had bacon, or the fowl, if you had chicken, or the peanut, if you had peanut butter, is not human. So your body basically breaks all that up and then reassembles it into human form, your human form, because we all have slightly different mutations, but for the most part, all of our hemoglobin looks identical for human hemoglobin, okay? Unless you have sickle cell trait or something like that. Yeah, Eve?
What's the bottom reaction called, and what type of reaction?
Of which one?
The bottom, the NaOH.
That's the modification. This is the same as, so this is base hydrolysis.
Okay.
Or saponification. So if you take sodium hydroxide and you actually take like a dilute sodium hydroxide 1 molar and actually get your finger in it and rub it around, your finger's going to start to get warm and slippery because you're actually converting the proteins in your skin into soap. You're making human soap. That's what you're doing.
It's like an episode of
Say again.
Breaking Bad.
Yeah, it is. Yeah, it is. Also what they did in concentration camps. There was another, yeah.
Oh, no, it was the same.
Same thing. What's the name of it? Yeah. Okay. Okay. All good? Okay, so let's practice one. Make sure that, again, the way you'll see this is, again, in the form of an actual compound. What are the products from that? Name the reactant, draw the products, name the products. Okay, looks like people are tracking. Special bond is right here. All right, that's the one both does the chemistry and the nomenclature. So this is going to be N-propyl. Butanidine. Okay, that's the starting compound, which tells me that it's going to make propylamine and butanoic acid. Good? Yes? Good.
Propylamine,
Propylamine, yes.
but it's not protein.
Its products are propyl, so propyl with a nitrogen is propylamine.
Two separate.
Yeah, yep, you got it. So if I drop propylamine, propylamine looks like this. Okay, this is propylamine. And amines, you can actually name amines either way. They're named both ways as the carbon group. Sometimes the carbon group is going to be the parent, sometimes the amine is going to be the parent. They're actually really low in the nomenclature world. So typically, you can also name this aminopropane. Both of them are accepted, all right? Because the amine literally is like a methyl group. It's just not a, it doesn't have a lot of weight in nomenclature world. So those are both accepted. And then I'm going to get out butanoic acid. So this is going to be butanoic acid. Okay. Yes?
Why is the NH2 on that side of the?
It doesn't matter.
Oh, it doesn't?
Nah.
Okay.
Nah, you can draw that wherever you want it.
No, I didn't feel
Yeah. You just flip it across the horizontal. Yeah. Okay. So what happens with amides and esters is, again, whether it's a carbonyl oxygen for an ester or a carbonyl nitrogen for an amine, that's still our special bond. Okay? Carbonyl heteroatom, nitrogen or oxygen, becomes the amide or the ester. Okay? Questions on that? Because yes, we're going to complicate it. We're going to add to it. We're not going to complicate it. We're going to add to it. And here's why we're going to add to it. Because esters and amides have another form that I think is really cool. The other form for an ester is a cyclic ester. Okay. So the cyclic ester is called a lactone. Right. And specifically, this is a beta lactone. And the beta comes from the fact that off the ipsocarbon, or the carbon of interest, I have carbon 1, carbon 2 off of the carbonyl. See that? This is the carbonyl. This is my special carbon. Always will be. This is my alpha and this is my beta. And you literally just use Greek letters to describe those as they come off. So that would make this again, here's my special. And so this is an alpha, beta, gamma. So that would be a gamma lactone. Okay. So what do you think this is going to be? Anyone? Alpha, beta, gamma. going to be a delta lactone. Okay. And so that's just a family of lactones. Lactones are cyclic esters. Okay. And so with this whole idea of cyclic functionality, this is where we get into an area of chemistry that I find deeply fascinating for a couple of reasons. One, the chemistry is very fascinating, but the other reason is it's probably in the pantheon of organic chemistry, it's probably, I would argue, other people argue slightly differently, but I would argue as an organic chemist that it's the most important molecule ever discovered. So this family here is going to be not a lactone like a cyclic ester, but a cyclic amide is a lactam. Okay, lactam. This is a cyclic amide. This is a lactam. So this is going to be off the carbonyl here. That's my special carbon. So that makes this alpha beta. This is a beta lactam. I can do the exact same thing as I did over there. This is going to be alpha, beta, gamma off the carbonyl. So this is going to be a gamma lactam. And finally, if I have a 6-membered ring, this is going to be an alpha, beta, gamma, delta lactam. Okay, and here's why this is important to us. Again, I would argue the most important molecule ever discovered looks like this. Okay. This molecule was discovered in the 1920s by Alexander Fleming. Some of you might know of him. Alexander Fleming was a biologist studying bacteria, and he was working with some petri dishes on some strains of bacteria. And being a good scientist, he did not do his dishes. This is in England, and he went on holiday to the ocean, and he came back after a week in the muggy summertime of London, and he noticed that some of his bacteria had a ring around them that something had killed them. So, being a good inquisitive scientist, he isolated what that ring of death around the bacteria had, and it turned out to be this molecule right here. Anybody want to take a stab at it? That's penicillin. So this is penicillin G. Okay. Arguably the most important, I don't know about important. If you think humanity's survival is important, it's arguably the most important ever discovered. I personally do think humanity's survival is important, so that's why I would put it as number one. Okay? Because this is one of those places where you literally can look at the person on your left and the person on your right, between the three of you, one of you in this room would not be here. One of the three of you would not be here. A third of the people on planet Earth would not be around today had it not been for the discovery of that molecule. And that's real. That's a real statistic. Okay? That's not just one of those, one of you look to your left and right, one of you won't be in this class at the end of the semester, right? We've all had that calculus class.
So what about a penicillin?
Yeah, and so I'll break that down for you. So this is the original. This is the, and here's why I talk about this. And I'll show you a couple other ones, ampicillin, amoxicillin, and those. This is the original penicillin. Once we have the original, just like with morphine, that's what nature, nature capital N, made. Then we synthetically go in and modify it, try to figure out, can we make it better, can we make it worse, can we get rid of side effects, and all that kind of stuff that we've talked about. This is the original. But the reason why I bring this up, what type of a lactam is that? It's a beta lactam, because here's my special carbon, and it's an alpha beta that comes back to the nitrogen. So the penicillin family is the beta lactam family. And here's the science behind it. It's amazing what happens with this chemistry-wise. What happens with amides? Oh, they break up with their special bond. And so what happens with this actually bonds to the cell wall of the bacteria, which causes it, keeps it from reproducing. That's how they actually react. Special bond reacts to one of the amino acids in the bacterial wall. So that's why some of these are very unstable. Some of the higher potency penicillin family cillins, you actually have to keep them cold. They have to be stored in refrigeration because that bond is so hot it wants to open up. And so they decompose pretty quickly.
What keeps it from bonding with your own cell walls?
It does.
Oh, okay.
It does. But again, it's at a dose that's specifically the way it fits into the binding site of bacteria. Remember, bacteria is smaller than us, so it actually affects it more than it affects us.
So is the way that it binds to bacteria so effectively what makes it such a widely used, like, general spectrum antibiotic? Because I know
Yep.
in the military we use it for everything under the sun.
Absolutely.
That's like the go-to.
Yep, and so it specifically targets bacteria, but even the good bacteria in the gut, right? We have bacteria in our gut, and it kills it as well, right? Which is why after you're on a dose of penicillin, you probably should recharge your digestive enzymes. Because it does, it's not specific. It just loves that bacterial wall. Okay, so here's the thing with the different cillins. Adam, you might help me. Do you remember when you were a medic which one is, one's IV and one's oral, and penicillin G and penicillin V? Do you remember which one it is? I don't remember.
I've actually never seen it IV. We actually had a solution which we named the peanut butter shot, which came in a ginormous syringe and it was super thick.
Super thick?
And it went into the butt cheek.
But it did. So that was okay. So one of them, I think, I'm not gonna guess. One of them's oral, and one of them's IV or a shot. The difference between them, this is penicillin G. Penicillin V has an oxygen here. That's it. So it literally puts an oxygen there. All right, that's the difference. Making one orally available, one injection or IV available. Okay? So that's the difference between those. Now, when you get to the modification that chemists have done, you get one that you might know of with a nitrogen here. And what's a nitrogen called? Amino. So if you put a nitrogen on that carbon right there, it becomes aminoacillin, ampicillin. So ampicillin puts a nitrogen on that carbon. And if you leave the nitrogen on that carbon and you put a hydroxyl group on the aromatic para, the para position opposite the carbon, the ipso carbon, this becomes aminoxacillin, amoxicillin. okay? And that's where the names come from. They're just modifications of the original. They're synthetic modifications, and there are dozens of them. In fact, some of the newer hot ones that have come out, instead of having a 5-member sulfur ring here, they have a 6-member sulfur ring. And they're kind of the newer class of silins that are coming out that are we're showing to be.
So is Rocephin a derivative of this, or is Rocephin itself?
No. That is a really complex structure. I can't draw that one. It has like 13 chiral centers to it. It's really complex.
I know Rocephin was the second one you used to do penicillin, and it was the same.
Yeah.
You had to go with the budget.
Yeah. That's a really complex. It's really complex.
Those are the ones that was discovered on, I think it was rotting grapefruit.
I don't know about that one. I know one was found in the sewers of France, and that's the one that actually has the 6-member ring over here on the sulfur. It was found in some sludge, which is interesting, some bacteria sludge in the sewers of France, and they actually isolated it. It turned out it was a new hot class of penicillin found. Kind of funny where we find these things. Coral sponges, like the toxins that you were talking about. Okay? So, yes?
Does grapefruit react with some medication?
Yeah, no, I don't know the answer to that. I have a buddy who's had 2 kidney transplants. No, he's had a liver to kidney transplant, and he can't have grapefruit because of the medicine he takes. Yeah, the anti-rejection medicine. And I don't know what the chemistry is. In fact, I should figure that out because it is real.
My husband can't have it either.
Is that right?
His heart medication.
For his heart medication. Yeah, I'm not sure. I'll find that out because I should know that. I just don't. I don't know what the interaction is there. I mean, I don't know why it's specifically grapefruit because all citrus have citric acid in them, but there's something about grapefruit that I'm not sure why it's just grapefruit. You can still do lemon and orange, but why not grapefruit? So I don't know, but I'll find that out. That's interesting. Okay, so our last compound for the chapter before we crash the plane. These are so when the body and so here's where we're headed. This is our last lecture of organic chemistry. There'll be some tears from some, and there'll be some elation from others. Yeah, right? So we're moving out of true organic chemistry into biochemistry on Wednesday. We will still see organic molecules, because biochemistry builds on bigger organic molecules just get bigger. All right, so we're just going to have more time at the whiteboard drawing molecules. How fun is that? I love it. But it's going to be more molecules that are this category. They just get big. All right, so we're moving out of carbon organic molecules to bigger bioorganic molecules. Okay, so we're going to start talking about things like lipids, proteins, enzymes, right? And we're going to see how this actually functions when we take something like cellulose and break it down and extract the energy and the electrons from glucose. We call that the citric acid cycle. I learned it as the Krebs cycle with the citric acid cycle. Okay, so we're moving into biochemistry, biology chemistry, right? We're in that kind of that la-la land between organic and biology. So where Dr. Chase lives, she's a biochemist. So that's kind of a fun transition. We will actually pull up the old PowerPoint to show a few of these molecules because it's really hard to draw 10,000 amino acid protein on the whiteboard. You probably wouldn't want me to do that anyway, so we'll actually show a picture of that one. But the last thing that's very fascinating as our final understanding of the nitrogen-containing compounds of carbon. There are 2 amines that have to do with the degradation of tissue. Okay? When the body is alive, when we are alive, we have something called our immune system. Okay? And our immune system is constantly pushing back on death. So when we actually die, by the way, the biochemistry between someone who has just died and someone who is still alive is identical. They're still in enzymes are still working. Oftentimes their brain waves are still moving. They'll kick or they'll twitch. Their body is still, but something has left them. What is it? I believe it's our spirit, but that's a metaphysical conversation. But there's definitely something that has left the person to cause them to no longer be alive. In fact, that's why we say search for signs of life. We don't search for signs of death. Because if you don't find signs of life, the opposite is death, okay? But once that process, once the spirit leaves, not the soul, the spirit leaves the body. We're triune, by the way. If you take the biblical model of humanity, we are made in the image of God who is 3 in 1. We are also 3 in 1. We have bodies, we have souls, which is our mind, will, and our emotion, and we have spirit. Okay, we are a triune being. We're different than the animals. Animals have souls and bodies, they don't have spirit. Okay? So we can talk about that later. And angels or angelic beings, yes, I do believe in them, as Jesus did. They are spirit and soul, they don't have bodies. All right, but we are triune. We're different than the animals, we're different than the angels, because we're this image of God thing, which the angels are like, huh? These people are weird. So when the spirit leaves the body, permanently, not temporarily, permanently, the body then begins to degrade. Has anybody been in the presence of a dead person? What was the number one thing you remember?
The cheeks swollen.
What was it?
Their cheeks swollen.
Cheeks are swollen, okay.
Cold.
Cold, yeah, that's,
Well, it depends on how long they've been.
yeah, how long they've been dead. Yeah, cold.
They were purple and their eyes were open.
The eyes were open. How long have they been dead?
Technically, he wasn't dead. It was in the
Wow.
middle of his heart attack,
Wow.
and then he was going doing CPR, and then at the hospital, he's like, "I saw you do CPR." And I was like,
Holy smoke.
"Shut up."
So he survived?
Yes.
Oh,
That was my husband.
that's your husband? Wow, holy moly, yeah, you told me that story. Wow, that's crazy. Anybody else been in the presence of a dead person? Yeah, what was it?
Rigor mortis, but that type.
Stiff. Yeah. So when I was at Point Loma, I was a biology major as well. I was a chemistry and biology major. That's a dual major. And we were in lab. I was actually in lab with Dr. Chase. And someone said, hey, there's a floater just washed up on the shores of Point Loma. We're all so excited. We're all biology geeks. And so we all bombed down to the beach, going down to Young Hall. And the number one thing I remember was the absolute intense stench. I could not get that smell out of my psyche for weeks. This has been a floater for weeks. This guy was in pretty bad shape. But the smell of decaying flesh was one of those smells that I can't describe. And here's why I bring this up. When the body decomposes, it decomposes from the inside out. When the immune system stops, we start to decompose from the inside out. We're already walking dead. Okay, when the immune system is no longer, then it takes over. And the two molecules from the organic chemistry perspective are these two here. This is the degradation of human flesh, or all flesh. Okay, this is called cadaverine, and this is called putrescine. Want to take a gamble at why their names are that? Well, it's because they smell horrible. And amines are amine bases, and they also are the smell of so my dad was a commercial fisherman. The smell of fish, my dad always smelled like fish. This is just because he was always around salmon. All right, so that smell, that aroma, is the aroma of death, which comes from the degradation of flesh, and it's these two molecules right here. I had a colleague in graduate school who had done 2 tours of Vietnam as a medic. Talk about pretty intense guy. And he had gone back after his 2 tours and went to graduate school. And so he was my lab mate. He had the awesome idea of buying these molecules from Aldrich, because you can buy them, they're just molecules. And he was really into photography. So he put these molecules on himself, and he took his big photo lens, and he was gonna take pictures of the California condors. And because what the California condor does in any birds of prey, they actually can sense this at about 1 part per million, 100 million. So that's what they're actually scent. They have a scent they have a nasal scent on in their membrane, and that's why they're circling. They can actually smell these molecules. They sense those, and so what they're doing is they're circling in on where it's coming from. And so he's lying there with his camera, but the birds would never come down. And so because he was actually in his camouflage tent, he realized, oh, I'm in my tent. That's why they're not coming down. They don't see the actual body. So Dave, smart guy that he is, hopped out of his tent. He's lying there on the ground with his camera. Sure enough, he's just real still. He has amazing pictures of his. California condors have a wingspan of like 12 feet. I mean, they're massive birds. And he has these pictures of these things just full on, talons out, coming down at him. And they actually started to land on him. I mean, he's got these pictures and they're just like, ah! So amazing. But he took those two molecules and was able to actually lure those birds in. So that's for the wildlife biology majors out there. So grab those molecules and you guys can do the same thing. So, okay, I will see you on Friday for our next chapter on amino acids. Your story yesterday reminded me of you used to say he was on, it was actually on a plane. He was a young guy, I got this a rock, the beds are, no, I can only do what I'm supposed to be doing. I was like, oh, please, crazy.
Oh yeah, we used to see that all the time. People, they try to train you, I'll get you a 10K superior if you just fail. Like, that's illegal.
Right. Just give me a little bit more, Yeah, that's crazy cool.
Or you have the old timers like the caddies and the old officers and be like, hey Doc, give me some of that some of that good number. So I can walk that out.
What do they want? Like oxy?
They want oxy, yeah. Or like Roxen. Like, no dude, come on man.
Give me a bottle of whiskey.
Like, no.
That's crazy. Anyway. No, you're good. Sorry, you're not being here last time. No, you're good. I just told you guys what you're doing here. You know, it's like, we're really like, you know who they are, so.
When is the next test?
It's after the. So we're gonna start new classes, so I want to encourage you to memorize them over spring break slides instead of. Come back, we have 3 lectures on it.
It's really huge.
So, are you gonna give me a ride to Bible study?
Oh, yeah. Oh, speaking of that, I'm actually preaching from the pulpit on Sunday. So, which is kind of cool, because I'm doing a Noah's Ark, this is really going to be, that's an extension of the flood.
Yeah.
So I'm going to review the flood, and I'm going to bring up, what about this boat? Genesis. Real,
And that's actually what I was gonna ask is, cause like, the way we're going in science, security, faith is actually kind of really starting to irritate me, because he's like, well, the DNA evidence suggests that Adam and Eve were never really a thing, it was a population of humans, therefore, what is original sin? Sin was before the fall. I'm like,
evil was before the fall,
right,
not sin. That's what we talked about.
yeah.
We
and
talked
I'm
about
like,
that at one of
makes
our
no
college
sense.
groups.
So like,
The Bible's very clear that they knew the difference. If they took up the tree, they would know the difference between good and
evil,
not
yeah.
sin. Evil. It's very important. There's a difference between evil existed before the fall. Sin is man's will and choice.
I just don't know where Adam fits into it, especially like with the
Go with
DNA
Paul.
evidence.
Don't go with Baker, go with Paul.
Yeah.
Paul was convinced that Adam was a real person, therefore Jesus had to be a real person. If
Yeah.
Adam was mythical, then why did he need a real Jesus to take away sin?
Exactly. That's my problem.
Okay.
Honestly, I think he's an okay guy, but he really
Just
is sometimes.
remember, everything on campus, even with me, that's that person's opinion.
Yeah.
You are here trying to synthesize which one is, remember, it's just a story, right?
Yeah.
Stories are based hopefully on some level of logic, some level of reasoning.
Yeah.
Which ones are more logical, more reasoning? Which ones have more evidence on which I can stand?
Yeah.
That's what you're trying to decide, not,
Yeah.
he's standing on, he believes it, I stand on something very different.
Yeah.
And I'm okay, he knows that, we have cordial conversations about this.
Yeah.
So-
But anyway, oh,
So,
yeah,
I gotta run the board.
You know what the worst smell in the world is?
No.
Yeah.
Well, as bad as,
And I get
Uncle
people
King,
that
burning flesh.
I was gonna say bioethical, but
We had one kid who came into the ER in Guam who was climbing a tree to eat fruit and he lost his balance and grabbed a power line.
Back at home.
So I saw my first electrocution. Literally, you can actually see it. Yeah, but we had to like still code him for the parents' sake. But like,
Do you have a
I would never know that life.
It's a gas log.
You could literally see like
I'll make it
the
happen.
electricity went in and traveled blew the body and like blew out the souls. It was like
Silverado 1500.
like just veins exploded. It was
Oh, you actually get a lot better.
it was.
Okay.
Whoa.
I don't even
You
want
never forget the smell of blood.
No, no, and I'll never forget the smell of that floater.